introduction. And today it's my turn to introduce our study. The title is the flow deformation interaction in rendering heterogeneous cross media. And the original speaker should be Professor Kuo-Chin Hsu. However, he is in the University of Arizona in the United States for a half-year show visit. And it's my honor to represent him here to present our study here. And Professor Kuo-Chin Hsu is my PhD advisor, and I graduated in 2009, and I am now working in a Geo-Resource Research Center in National Shih-Jung University. And first of all, we would like to thank the Institute for supporting this study. They are National Science Council and Central Geological Survey and the Water Resource Agency. And we very appreciate their financial support. Okay, let's see the outline. Today I will introduce the 4 parts. The first is the introduction, and I will introduce why we do this research. And also I will introduce what is the couple behavior or the couple phenomena under a pumping condition. And then I will introduce the stochastic poroelastic model. We use the poroelastic theory. It is proposed by built in 1941, and we also introduced a stochastic approach. We call it the first order second moment method, and it is combined to be the stochastic poroelastic model. And then I will show some results and discussion. And here I will separate to 2 parts. The first is the phenomena of the start of pumping. We will call the effect called the Nordenstam-like effect. It is very similar to the Nordenstam effect. I will introduce for this phenomena. And then we will see the stop of pumping behavior, and we call it the red light effect. Then is the conclusions. And the introduction, the interaction of the flow and the geomechanics within porous media is complicated processes. And for example, we have a change in water pressure that will alert the state of the stress and resulting in the strength of the porous media. Whereas the deformation in porous media induces a change in water pressure and alerts the groundwater flow. And let's see some very simple example here. Let's see how they interaction. We have a porous media like here, and we have the solid phase or a white circle, and we have the porous phase with the wavy phase here. And if we drive a change condition at the boundary, and we will condense this porous media to become like this one. And then we can find that the porous phase is condensed. So from this simple case, we can see that if we driving for water pressure change, it will cause the deformation. And the deformation will also cause the change of the porous media and induce different condition for the water flow. So it's a very complicated process to evaluate the interaction behavior. And the velocity of the stress propagation and the groundwater flow in porous media are very different. For example, stress may propagate at several kilometers per second, and the flow rate of the groundwater in sediment sandy sediment is only about 10 to minus 4 meters per second. So we can see that it's a huge difference, about 7 order magnitude. So it's a very large discrepancy. And how this speed affects the interaction of the behavior. This is a very simple example. If we have a soil column here full of the groundwater, and then we have a driving discharge condition here, and then we can see that the soil column will have a deformation like this one, but we can see that the water is drained out close to the draining boundary condition, and the other side is under the original situation. So the differences is the differences of the propagation speed is very different. So we will imagine that here we will have some interesting phenomena here. And Gauss and Cheskakis, they published a paper in 1989. They set up 3 boreholes and setting the 6 pumping wells. They will try to observe some interesting phenomena here. And we scheduled their pumping test to be just like this one. We have a pumping well here, and we pumping water from the aquifer. And there is a epitop curve. And under a distance away from the pumping well, we will have a critical direction water flow. And the driving force is the discharge condition here. So if we see this area, we can imagine that we can expect that the water pressure and versus the depth should be just like this one, a continuous decrease. However, from the observation of the pumping test, you can see some place have a larger or increased water pressure, like this one. So we call this to be the reverse behavior. And this reverse behavior is have to be detected by the coupled system. And if we use a uncoupled system, we cannot see this behavior. And let's see some observation data here. The first is the pumping test. We have the pumping start behavior. There are 6 pumping wells, and they have the this one is the groundwater head, and this is the time axis. And we can see that at different depths, we have the pumping situation. The P17 means the pumping depth is at the 17 meter, and the other, like this one, 52 is at a depth of 52. And they use the observation wells at the distance at about 43 meter, a little bit short distance from the pumping well, and they can see that there are some pressure or water head increased in the initial period. So this is we call it the reverse behavior. And this reverse behavior is first observed in the Notogang site. So we call this behavior to be the Notogang effect. And the other situation is the pumping stopped behavior. This is also the pumping wells. When we stop the pumping, we can see that there are some place, there are some water drop down in the initial period. So this is also a reverse behavior, and then water head will recover to the stable condition. And this effect is first observed at the red site, so we call this the red effect. And the behavior is from what mechanism? We cite the Kim and Perizek, and I'm not sure here. Okay. And they published in 1997 and 2005. They explained the Notogang and red effect is caused by 2 hydrogeomechanical mechanisms. The first is a slower hydraulic propagation of the pumping stress than its mechanical propagation. So you can see that it is the difference is because from the propagation is very different. And also because they are use a layer system, so they have different explanation. And also we can see that they mention that the relative lower hydraulic conductivity will cause the observation for the reverse behavior. And the second is the amplification of the faster mechanical propagation in the lower part of the equator due to its relative higher deformability. And we think that the first one is the main mechanism because it is more easy to reduce the behavior. So we are thinking that if we can use the solid phase and the fluid phase to detect or to observe the behavior using the correlation behavior. So the correlation behavior can be calculated from the covariance function, and we see that covariance function is identified like this one. We have two variables A and B. They are placed at different place and the different time situation. And we are interested in here. If A not equals to B, we call it the cross covariances. And the cross covariances can be calculated to be the cross correlation like this, CPW, and divided by the bilayer variances. So if we can use a covariance function to describe the correlation behavior, and maybe we can use it to explain the reverse behavior. So we introduce the stochastic approach. And let's go back to the conceptual model. This is the pumping well here. It's pumping the aquifer, groundwater from the aquifer, and we focus on this area for a one-dimensional case. And we set up the boundary at the top to be the free drainage condition and the free deformation condition. And at the bottom, we have a discharge condition and a fixed displacement. And we set up the data at the top boundary to be z equals to 0, and the z increase with the depth. Okay, let's see the basic physics theory. This is the governing equation for the elastic theory. It is proposed by Biot in 1941. We have this equation. We have the displacement at three dimensions, and also the change in water pressure. So this equation, exactly, they include three equations here, and the other is from the mass balance, derived from mass balance. We also have the change in water pressure and the deformation. So we have 4 equations here and the 4 variables here. But we simplify to one-dimensional situation to see if we can detect or observe the reverse behavior. So we simplify to the one-dimensional case. We have the vertical displacement and the change in water pressure. And this is a coupled system because we will solve it at the same time. And then we introduce a first order second moment method to separate the governing equation to be the mean equation and the covariance equation. The mean equation is just similar to the original governing equation, and the covariance equation is also very similar to the mean equation, but we have different type. We have the covariance function here, YW and YP. Here, Y is natural log hydraulic conductivity. And we also have a sink and source term here. And in this equation, we would like to solve the YW and CYP, but we have to include the CYY, the covariance of the natural log hydraulic conductivity, and also the mean of change in water pressure first, and then we can solve the CYW and YP. Later, I will show the reverse behavior in a solution of the CYP. Then we have another covariance equation. Here we have WP and CPP, and CWW and CPW. And the CPP we can calculate to be the variance of the change in water pressure. We can use this equation to evaluate the uncertainty of the system, like the change in water pressure and also the displacement. And here we're interested in this item, CPW, because we think that the reverse behavior is caused by the interaction of the water pressure and the displacement or the deformation. So we will solve the CPW to see if we can observe some phenomena. And in the numerical implementation, we use a fully implicit finite difference method, and we use the mesh center approach. The central difference is for the spatial discretization, and the backward difference is for the time deviation. And here is our time difference equation. And then we, from the previous equation, we have a bandwidth matrix, and we use the Thomas algorithm to solve this couple system. So we can eliminate the upper part of the matrix to be like this one, and can recalculate the variable of the S variable from this equation. Okay, let's see some result and discussions. The first I would like to show is the heterogeneous cross media. In this study, we also use Monte Carlo simulations. The Monte Carlo simulations have to input the realization. We use hydraulic conductivity to be the random variable. So we use the hydraulic conductivity realizations to calculate 8,000 realizations. And here we show 4 realization result. This is hydraulic conductivity versus the depth. So we can see that the hydraulic conductivity is very noisy, very large. And from the calculation, we can see that the displacement is very smooth, because the displacement is the accumulative displacement, and the water pressure change is a little varied, because it's the point water pressure change. So it's a little different, but we can see that the heterogeneous is very obviously. And then let's see the mean and the variance of the variables under a pumping condition. And we are thinking about that if there are no reverse behavior. The upper figure is the mean displacement and the mean change in water pressure. And the value of in the figure is the dimensional depth. The 0.25 is shallow depth, and 0.5 is at the window depth, and 0.75 is at a deeper depth. So we can see that the displacement do not show any reverse behavior. And we can see that the mean change in water pressure also do not show very obviously reverse behavior. However, if we see very closely, we can see that at the shallow depths away from the discharge condition, it seems to have a little delay of the change of the water pressure. And in the balance of the displacement and the change in water pressure, we also cannot see any reverse behavior. So let's see close to the change in water pressure. This is the dimensional depth, and we can see at the 1 minute, they have a very smooth curve here, and this period, this depth is not caused by the change condition, because the water flow takes time to change. So we see a little differences. And if we look close to the displacement, we have a normalized displacement here. We can see that there are a little abnormal behavior. If we calculate the deformation of each element, then we can see that from different depths, from 0 to 0.5 depths, we have some positive and negative behavior. And the positive means the expansion, and the negative is the compression. So if we see closely, this is a expansion condition and cause the water pressure drop. So this is a very interesting behavior here. And then we see the covariance of the variables under pumping condition. We call it a norm-like effect. This is for the CYP versus time, and this is for CPW versus time. So we can see that at the initial period, we have a negative YP value, and then it will go back to a positive value and reach the stable condition. And also we see the CPW, they have a very slightly positive value and then go back to be the negative value. So we can thinking that means the positive means the P and W have the positive correlation, and the this fluctuation is very similar to the observed reverse behavior. So we call it the non-gum-like effect. Let's see more detail. This is for different depths, and we calculate, use the Monte Carlo simulation and the first order second moment method. At the initial condition, we have a soil column here, we have a uniform water pressure. And then if we use a discharge condition here, the water should be like this one. This is change very fast, but at the top boundary, the water will not change so fast. And if we simplify to the very simple case, we like this one to separate to two parts. The upper part is not changed, the water pressure is not changed, and the low part is decreased. And theoretically, we observe the behavior is the element at the top boundary is expansion condition. So the deformation is the sediment is decreased because we use a positive for the compression. So the expression means the decrease of the displacement. And then you can see that the pressure is also dropped down. So under this condition, we have a lower water pressure, and expansion means the negative sediment. So we have the positive correlation here. And if we calculate the maximum CPW value versus the dimensional loss depths, we can see that there will be some maxima at different depths. And this behavior is very similar to the observed data, like this one. So they also have different depths, and they have also have different maxima values here. And we can also fitting that they are just like this one. And so there will be some limitation of the detailed behavior. Then we are thinking that a situation can reverse phenomena occur. So we use the sensitivity analysis to see if we can see some behavior. The first, we evaluate the hydraulic conductivity. We set it to be more larger and more small. The original setting is 10 to minus 5 meter per second. So you can see that a larger hydraulic conductivity will show no reverse behavior. And if we use a small hydraulic conductivity, the reverse behavior is very obvious here and here. However, we cannot see that if they reach a stable condition. So we calculate, this is the same case. We calculate different period for a long period. We can see that they will reach a stable condition here for a positive. So the negative behavior is the reverse behavior. We can say that. And also we see we use the Young's modulus to be larger and smaller. We can see very similar behavior. So a small Young's modulus will cause the reverse behavior more obviously, like this one. And then we will evaluate the red light effect when the pumping is stopped. So let's see. The upper is the mean solution. We have the mean displacement and mean change in water pressure. So we stop the pumping at the 30 minutes. So you can see that the displacement is decreased very immediately, like this one, at different depths. However, if we see the change in water pressure, we can see that the press close to the drain boundary, they will increase very immediately. However, if it is away from the drain boundary, they will have a delayed behavior, like this one. So this is just like this behavior we call it a red effect. And also we evaluate the CYP and the CPW under a pumping under stop of a pumping condition. So we can also see that there will continuous increase or continuous decrease, and then go back to the original condition. And how about recharge? Previously we just use the discharge condition or the pumping condition. How about discharge? Yeah, we can see that the behavior is very similar. Here is the mean displacement and the mean change in water pressure. So we can see that just the different sign. So this is minus and this is plus. So you can see that the behavior is very similar. And then we have some conclusions here. The reversal of the cross covariance was found for the case with a pumping and a stop and the sudden stop of pumping at the boundary. And the second is a lower hydraulic conductivity and a small gas modulus that will lead to most significant flow deformation interaction. And the third is the responses of the deformation and the point pressure in the porous media with flow deformation interaction are the result of the computation of the propagation velocity of the stress and the water flow. This is just like the Kim and Perry-Jack they conclude. And then the magnitude of the flow deformation interaction in a randomly heterogeneous system depends on the temporal dynamic and also the flow mechanic properties of the porous media. So finally, let's recall what I'm talking today. The first is what is the reverse phenomenon? I talk today is focus on the reverse behavior for a pumping condition. So a reverse means it's abnormal. It's not like what we expect. And the second is when does a coupled system work? From the references, they say that the coupled system should be observed under a multi-dimensional condition. However, in our case, just a one-dimensional case, we can also see the coupled behavior. And the third is where is to use the pro-electric theory. If we have any solid phase or fluid phase, we can use the pro-electric theory to explain the behavior. However, the pro-electric theory is very have different type of the modeling system. There are some plastic or some other thermal condition here. They use different type. And finally is how to evaluate the cross correlation. If you want to evaluate the variable with the cross correlation, you can use a stochastic approach. It will help you to understand the interaction between the variables. And thank you very much for your attention.